many times when we'll take measurements, we want to be able to figure out the mean value for a system. And typically, the system's mean is not going to be the same as the mean of our measurements. So we want to be able to estimate the population mean. Here, for example, is some population of a random variable, and it has mean 5 and standard deviation 3.16. Say we take a sample of that, where n is equal to 3, little n is 3. So the sample size is 3, and the sample mean is 3. Now we know that the sample mean is only an approximation for the population mean. You can see here that they're not equal. What we want to be able to say is that we want to be able to draw some conclusions about the population mean from the sample. So we would say that we think the population mean is within the range of the sample mean plus or minus some value delta. We could rearrange that, and the same assertion is that sample mean minus delta is less than or equal to population mean, which is less than or equal to sample mean plus delta. For example, xm minus 10 is less than or equal to mu, which is less than or equal to xm plus 10. This is the same as saying that xm minus mu is less than or equal to 10. And with that range, we want to be able to say, assign some value of certainty to it. And the names for these terms the names for these values are confidence interval, which is the range of values that we're claiming for our population mean, and the confidence level, which is the certainty that we associate with that confidence interval. A different confidence interval could be xm plus or minus 2. So we're saying the population mean is somewhere in the range of sample mean plus or minus 2. Now, how do we compute the certainty, the confidence level for such a confidence interval? Well, whenever we take different readings or different samples, we expect the sample means to be different. So here's another sample, and it has a different sample mean, and here's another sample, and it has a different sample mean. And each of these samples is going to have a different sample standard deviation. But we can apply the central limit theorem to draw conclusions about the population mean. The central limit theorem says that the sample means follow a normal distribution under one condition. First of all, that they follow a normal distribution means that if we take a bunch of samples and take the means of those samples, then those sample means are going to be random. The sample mean is going to be a random variable, and it follows the Gaussian function. And that's true as long as the sample size is really big, so as n approaches infinity. But for most cases, we can say as long as n is greater than 30, then we can apply the central limit theorem. Or, in other words, the sample mean is going to follow a normal distribution. There's another case in which we can apply this, and that's if the population itself is normally distributed. So if we know that this population follows a normal distribution, then the sample means will follow a normal distribution, even if the sample sizes are small. But typically, we don't know the statistics of the population. So let's define a couple of new terms here. We have mu sub m, which is the mean of the sample means. And if this condition is met, then that is equal to, well, actually, in any case, the mean of the sample means is equal to the population mean. And here is where we have to have a large N to say that the sample standard deviation, the standard deviation of the sample means is equal to the population standard deviation divided by the square root of the sample size. That was a mouthful. And we also have a variable change because if the sample means follow the normal distribution, then we can use the integral table to find out probabilities for different population means. So we want to have this variable eta, which is defined as this ratio here. We have the sample mean and then the mean sample mean and the sample mean standard deviation. Substituting in to this, we get that we substitute in for mu and sigma over square root of n, and then rearrange that to look like this. So we have this new variable eta, which is in terms of the sample size, population standard deviation, and population mean. Now, back to the question of how do we figure out the confidence level. Say we have a sample with 33 measurements. The sample mean is 5.33 and the sample standard deviation is 6.92. Now we assert that the population mean is in the range of sample mean plus or minus 2. And what's our confidence level for that? So we'll step through that. Again, we have the variable eta because we want to use the integral table for the Gaussian distribution. Here, sigma is not known, neither is mu. Sigma, we're going to use the sample standard deviation as an approximation. And we'll rearrange this assertion in this form so that it matches up with this equation for eta. So what we're saying, in other words, is the absolute value of the difference between our sample mean and the population mean is less than or equal to 2. So we're going to substitute 2 here for the difference between our sample mean and our population mean, because we want to find the probability that eta ranges from a certain value to another value, and that's the same as saying that this difference ranges from negative 2 to 2. So we're going to go ahead and substitute in 2 for this value. And what we come up with for eta here is 1.66 using the numbers given for this problem. Now we turn to our integral table, and we know the value for eta from this equation, and we want to find out the probability that eta is going to be within that range. So if eta is 1.66, then the area under that curve, or the probability that eta is between 0 and 1.66, is 0.4515. So the probability that eta is between negative 1.66 and 1.66 is 90.3%. Again, we use the variable eta because that enables us to employ this integral table, but eta is related to our system through the sample size, sample standard deviation, and this delta that we have here. One other way of looking at this is that we have 9.7% uncertainty, and that introduces this term level of significance, and it's given the variable alpha is associated with the level of significance. So 90.3 is 1 minus alpha, and that's a variable that you'll see often associated with these confidence levels and confidence intervals. Again, just rewriting how we figure out eta for these cases. It's square root of n times delta divided by capital S. And delta here is the range. Remember, we said that we thought that the population mean was within the range of x plus or minus delta, x sub m plus or minus delta. Another problem that we might want to do is if we know the value for eta, so if we know the confidence level that we want, and we know the sample standard deviation, sample size, this can give us the confidence interval. So this can give us the value of delta if we just rearrange these equations. So let me do an example of that type of problem. say for this example, we have a batch of resistors. And out of this batch, we've measured 36 resistors. The average of those readings is 25 ohms, and the standard deviation of those readings is 0.5 ohms. What we want to do is find the 90% confidence interval on the mean resistance of the batch. So we want to say with 90% confidence what the interval is, or what the range is for our batch mean. So what we're looking at here is a normal distribution, and this is on the variable eta. So the mean is for eta equals 0. And we want to find the values of eta that are in the shaded part. And the area here is 0.9. So there's a 90% chance that the values that we're interested in for eta are in, there's a 90% chance of getting the values, the range of values of eta that we're interested in. So we'll call this eta sub c. We want to find this value of eta, and eta sub c for confidence level. And we know that the area from our tables, our integral table gives us values for area from 0 to eta. So again, the integral table will give us this area here. And that area is 0.45, so it's half of this total area. And now, if we look at our table, okay, so we wanted a value for A to be 0.45. So looking here, here's 0.4495 and 0.45053. So we know our value for eta is between 1.64 and 1.65. And we can interpolate, do a linear interpolation to get that value for eta. So eta minus 1.64 divided by 1.65 minus 1.64. So the differences in eta values is equal to the difference. Now we have the difference in area values. 0.44950 divided by 0.45053 minus 0.44950. And this gives us the eta is 1.645. So if eta is 1.645, there's a 45% chance of getting a value between 0 and 1.645. Now that we have eta, we can use the equation for our confidence interval, where delta is that interval, and that's equal to the eta times sample standard deviation divided by square root of n. So for this example, we had 1.645 times 0.5 was our standard deviation, and square root of 36. So that gives us 0.137 for delta. The result is that we're saying our population mean, or the average resistance of this batch of resistors, is between 24.9 and 25.1. And we're saying that with 90% confidence. Now, the last topic is rejecting outliers. We have data points, and sometimes data points will look suspicious, and we want to know if that data point was really far from the others because of some error in the process, then we want to get rid of it. But if it truly reflects the underlying system, then we want to keep it. And so what we're looking for is some standard or systematic way of rejecting outliers. And there are many different criteria, many different methods. We're going to look at Chauvenet's criteria, which says that in order to keep a reading or a value, the probability of getting that value has to be greater than 1 minus 1 over 2 times n, where n is the number of readings. So for example, if we took 50 readings, then this difference here, 1 minus 1 over 2 times n, is 0.99. So if we took 50 readings, we would only keep those data points that have a probability of 99%. So if we get data points that are not within the 99% probability range, then we would keep it. Then we would reject it. So if we found a data point and there was only a 0.05% chance of getting points greater than that, then we would get rid of it. So this is done in terms of deviation. Well, I should say it can be done in terms of deviation. So we could look at each value that we took in our sample and calculate the probability of that value, of getting a value like that. And then if that probability is not within the range required, is not greater than 1 minus 1 over 2 times n, then we would get rid of it. Or a quicker way is to use a table like this and just look at the problem in terms of the number of readings, the deviation, and the standard deviation. So deviation is defined as the difference between a given reading and the sample mean. For example, if we had a sample with these readings, little n is 10, we have 10 readings, and the sample mean is 6, and the sample standard deviation is 3.37. Since we don't know the population standard deviation, we'll just use the approximation of big S for that. And the deviation here is just the difference between the reading and the sample mean. So we have 1, 0, 2, 0, all the way up to the 10th reading, which had a deviation of -9. So that seems pretty big, and we want to check and see if that or any of the others are erroneous or outliers. Now this ratio between the deviation and the sample standard deviation is given here for all the readings, and we want to compare that to Chauvenet's criteria. For 10 readings, sample size 10, then the maximum acceptable ratio is 1.96. 9 of the readings are less than that ratio, but this last reading has a ratio outside of the acceptable range, meaning that this is a bad data point. It's just so unlikely that we would get a point like this that we'll get rid of it. Now that we have gotten rid of that point in our sample, we need to recompute the sample mean and standard deviation. So we come up with these values if we got rid of that. And you can see a really big change in the sample standard deviation. So we looked at how to estimate the population mean from sample data, and also the confidence interval and confidence level for that estimate. And the final topic was a criterion for assessing whether or not a data point was valid.